Chalk Talk is brought to you by Isolite, the emergency lighting experts. Stay educated, my friends.
Good morning, everyone. Thank you for joining us for our June Chalk Talk. It's hard to believe that today is the last day of June, halfway through the year. Where has the time gone? I'm Western Regional Sales Manager Greg Keel, along with Eastern Regional Sales Manager Matt Bird, and thanks for joining us for our Chalk Talk. As you can see, our topic today is going to talk about transferring power and the ELCD devices and how they differ and how you can use them with our inverters. As always, our host is our Director of Product Development, Evan Ackman. We know this is a busy vacation week, so thank you for taking the time to join us wherever you are. Evan, take it away.
Yeah, count me amongst the people who just realized that today was the last day of June. So thanks for that reminder, Greg. And thank you guys for joining us here today. For those of you who have been with us on our Chalk Talks since way back, almost 3 years ago, you might say that this is a rehash of an old Chalk Talk. It's actually a rehash of the first one that we did. And the reason why we're talking about this, maybe most importantly, is I think we're getting a lot better at presenting this information. We've updated things, we've got better drawings, we've updated our white papers, but on those old Chalk Talks, we actually didn't record audio and video of them. So the record on our website is not as good. And so we're going to take this opportunity on this sort of week between the July 4th holiday and the week after Light Fair, where we thought attendance might be a little bit light. It doesn't look like that's the case, but we took this opportunity to redo it. And so we're going to go through this in a little bit of a different way than we did that first time. We'll start with a code refresher. This is going to be different than the code refresher we usually do because it's a little bit more pertinent for how inverter-based systems get deployed. We'll talk about these ELCDs in general. We'll talk about the difference between the ALCR and BCELTS. If those acronyms mean nothing to you, just wait a couple seconds and they will mean everything to you. We'll go through the wiring diagrams to show where these things fit in the architecture of an emergency lighting system. And then we'll end by talking about our offering, as well as some of the information that's been updated on our website. If you guys have questions, please throw them in the chat. We'll make sure that we don't get off of this call until everything is answered to your satisfaction. So jumping right in, usually we are talking about sort of illumination levels and 90 minutes and all that stuff when we're talking about code, but it's useful in this context to talk about what life safety code believes is an emergency. Now, the thing that we often think about as an emergency that we're trying to deal with when we're talking about emergency lighting in particular is a power outage. It's windy out or there's a storm, a tree falls, knocks out a power line, power's out, that's an emergency. And yeah, of course, that is one of the things that we have to tolerate. But the other thing that's a little bit more interesting and sort of maybe often ignored is even localized failures in a building have to be accounted for. And, that includes any way that sort of lights in a space would be accidentally off. So, if someone takes an axe and puts it through the wall, that's a localized failure. If someone sticks a fork in the outlet, that's a localized failure because the circuit breaker is going to trip. If the circuit breaker is turned off for maintenance that's going to impact the lights in that area, that is something that NFPA 101 considers an emergency as it relates to emergency lighting. And so we want the emergency lights to be on in that application. And what that really means for us, the brass tacks here, is that these ELCD type devices, they need to go as close to the lights as possible. They really want to be observing the power feed that goes to the lights, not the power feed that goes to the inverter. And that's that's one of the things that jumps up and bites people a lot of times. It can, in smaller applications, you could see ways where you would be able to basically take the inverter feed, run it to the ELCD, monitor that, and have the lights turn on in that situation. But that's not really code compliant. We want to be observing the power feed that goes to the lights. And you'll see exactly what that means when we get to the wiring diagrams. And I'll highlight that a little bit more there. And it has one important ramification that it's worth considering. In larger systems, as you get above 1,000 VA or more maybe, you may have systems or buildings that are not all in emergency mode at the same time. So you may have power to the inverter and the inverter is passing through utility power, but one half of the building is technically in emergency mode, even though it's not discharging batteries. This is a very good thing, and this is how we want buildings to operate, because you're basically using the best source of power available in that application. But it does confuse people to say that, oh, you could have a private office that's in emergency, but the other spaces are not. So it's important to keep in mind that that's a ramification of this this design and this requirement by code. Now, emergency lighting control devices, we really haven't defined them. We've sort of talked about them, but what these devices are they enable the general illumination, the architectural illumination, the lighting fixtures, to act as emergency lighting fixtures when there is one of those emergencies occurring. They're the thing that says, okay, right now you're going to be controlled by the lighting control system, and oh boy, there's an emergency now. We're going to override all of that, and we're going to drive these things on to full emergency light level. Now, the reason why this is a topic and it's not simple is because there's two different types of these devices. There's the automatic load control relay, and then there's the branch circuit emergency lighting transfer switch, abbreviated by ALCR and BCELTS, respectively. And this is sort of a source of confusion, and people don't really understand the difference when they are first a part of this industry. And so I want to just kind of nail this down, and we'll start with the definition by code. The highlights are mine, and then we'll do the plain English version. And so an ALCR is a device used to set normally dimmed or normally off switched emergency lighting equipment to full power illumination levels in the event of a loss of normal supply by bypassing, again, my highlight, but it's the most important word, by bypassing the dimming and switching controls, and to return the emergency lighting equipment to normal status when the device senses the normal supply has been restored. That is an alphabet soup of words, and the pigs and bunnies version of it is the ALCR devices override dimming and switching controls, and they require, and this is important, a normally on power source. So when you're specifying your inverter, that would be a normally on output. That's kind of the most common one. Let's contrast it verbally with the BCELTS, and then we'll get into the diagram. So the BCELTS is a device connected on the load side of a branch circuit overcurrent protective device that transfers, again, that's a key word here, this transfers only emergency lighting loads from the normal supply to an emergency supply. And that transfer word is doing a lot of heavy lifting in this definition. The plain English, the pigs and bunnies version is, this changes the power source that supplies power to a fixture. It converts a normally off source, like a generator or like a normally off breaker on an inverter, into a normally on source by selectively figuring out where power is coming from. And so a picture's worth 1,000 words. And so let's just jump right into it. Now, a couple things to keep in mind on this diagram. The way that this is architected is over here on the right side. This is a single zone, an architectural zone of fixtures. They're going to be controlled together in normal mode. And then there's only one critical fixture. If I sort of draw this dashed line here, there's one critical fixture here that is intended to remain on when there's an emergency. Now, what's going to happen here is when everything is okay, the lighting control, which I've drawn as a snap switch, obviously turns on the non-critical fixtures. And because that ALCR there is observing what the lighting control is doing, it's going to close its relay and pass that normally on power over to the critical fixture. All of this stuff works. Now, let's highlight a couple important things here. The first is we actually have two independent circuits at play here, right? We've got the dedicated circuit breaker for the inverter, and then we have the one for the lights. And what you can see here is that, as we said before, the ALCR is monitoring the circuit that is that's controlling the normal illumination fixtures in that room. And so the failure mode here, if this circuit breaker goes, if it gets opened or if something happens that it is not available, and I draw that, it's going to say, okay, we're in an emergency. I've noticed that from my sense line. I'm going to ignore everything. I'm going to close my relay, and I'm going to turn that critical fixture on. So even if utility power is still good, even if power to the inverter is still good, what's going to happen, the inverter is not going to discharge its batteries. It's just passing through utility power, but this fixture will be in emergency mode. Remember that key word I said, bypassing. It's bypassing what the lighting control is telling it to do. It's ignoring all of this stuff and just says, all right, I'm on, everything needs to turn on. So that's how the ALCR works. Now, if we go to the BCELTS, same thing over there on the right-hand side is one single zone of lights. The architecture is somewhat similar. I've drawn this with a generator to really nail down the fact that this is normally off, right? The generator is not operational when there's not an emergency, but everything else is kind of the same. We're monitoring the feed to the non-critical fixtures to figure out when we're in emergency. The behavior of this device is slightly different. So when we're in normal mode, the actual lights here, the critical fixtures are technically in parallel with the non-critical fixtures. They're connected to that lighting control. But what happens in the emergency, same thing. If we lose power to our non-critical fixtures, the BCELTS device actually totally isolates everything in the top half of this drawing from the critical fixture and the emergency system. It sort of disconnects it and changes the source of power. So in that application, or in this time, the generator is directly connected to the critical fixture. That's what we mean when we say it actually transfers power. There's two different sources of power that might be present for that critical fixture, depending on the status of the building. And now this is all well and good, but the obvious question is, who cares? They both seemed like they do sort of the same thing. Why do I need to understand this difference? And you do need to understand this difference because there's a couple different things to keep in mind here. The BCELTS will work in basically every application. You could replace an ALCR with a BCELTS, but there's a compromise there. And so if we sort of draw this 50-foot brick wall between them, the BCELTS, while it technically does more, it's a lot more costly of a device, sort of a factor of 4 or 5. It's also a little bit more of a complicated device in terms of how it has to get wired. It's a little bit more difficult to wire it in. It's a surface mount device, whereas the ALCR devices can mount in boxes. But it does give you a little bit more flexibility. It's compatible with more different types of dimming. You can have 2-wire dimming, 3-wire dimming, some sort of like power line carrier dimming based on it. Whereas the ALCR, it's an inexpensive and easy to get into a job kind of device, but it's really limited to 0 to 10 volt, Dolly ecosystem, DSI, PWM, low voltage type dimming systems. And so there is a trade-off there. We actually have an AIA course that goes into a little bit more detail on this particular distinction. There are ways to use ALCR devices with things like phase control dimming, but there's some trade-offs there, and it's a little bit more complicated that we can get into in a 15-minute course. So I'll talk a little bit more about that course at the end. Now, we make both different types of this device. The ELCD 924, this is actually a product we used to OEM, but maybe 2 or 3 years ago, we decided to make one ourselves because we thought we could build a better mousetrap, and I believe that we have done it. So our focus is really on simplicity and reliability. And so that is what this device does well. The relay inside of it is way oversized for the 20 amp circuits that it's going to be on. And we do zero cross switching, which means it's an arcless switching technology. And so that allows us to say this is a 1,000,000 cycle device. It will be the last thing remaining if there is an emergency in a building. It will always just work. But the other thing that we have as a benefit over what other people do in the industry is we kind of have one model to rule them all. If you look at some of the competitors' products, you have to pick different versions based off of the different mounting that you want to have. If you want to mount it on the surface, if you want to put it in a fixture, if you want to put it in a junction box, we put it outlet box. Those are all different model numbers. For us, it's all one model number. And we've kind of creatively designed some like snap tabs on the back. So in some instances, you'll just snap those off and mount it. Sometimes you keep them on and mount through it. So it's a really flexible product that mounts in all of the different ways with one single model number. And then we have the integration of fire alarms and dimming as an optional extra. Now, it's most people don't think that emergency lighting devices are super sexy, and that's true of ELCD devices. But if I had to pick sort of the device that had the least fanfare, it would be the ELCD 1008. There's not a lot of exciting things that happen sort of on this kind of device, but there are opportunities to be just better than everybody else. And so one of the things that plagues the competitors in this industry is they have sort of the mandate that you mount their devices into a 4x4 box and you use inline fuses that the contractor has to mount. And these are big devices. They're fairly complicated because of what they have to do. They potentially switch between, a lot of voltage between two different contacts, and they may not be synchronized in terms of the phasing. So they're kind of beefcake devices, and those inline fuses really protect the device. But because they're so big, and because you're like the competitors force you to mount it in a junction box, there may not be room. And so in the best case, the electrician's upset with you for specifying this because he's got to use his 18-volt DeWalt drill to crank it all down and use it as an installation device. And in the worst case, and the one that we sort of feared was happening the most when we OEM'd some of those products, was they were just getting ignored. And so what we've done is we've basically built an all-in-one box that has terminals that you don't have to sort of do flying leads to. You don't have to mount these external fuses. All the fuses are built into it so that it's always safe and easier to wire. It's a surface mount device. You can bring pipes straight to it instead of crank it into a 4x4 junction box. So it's easier to actually install, and it's always going to be installed safely. And then we don't play ratings and specification games, which sort of plague the industry, I would say. So it's 20 amps no matter how you want to get there. It's not 20 amps of resistive load, and then you got to derate it if you've got HID or tungsten or an LED driver or magnetic ballast. It's 20 amps full stop. And then because this is a Cadillac, because it's a tank, everything's just built in. So the fire alarm integration and the dimming integration, it's all just there. Whereas on the 924 type devices, the ALCRs, they're optional extras. And that brings us to the line that you can see right here. So I mentioned the ELCD has those optional extras. You can get it with a fire alarm or with a fire alarm and the dimming interface. And then the ELCD 1008, the BCELTS device, actually just has everything all in one. There's just one device. And that's it. All this information is already available on the website through our cut sheets. We have wiring diagrams. We have a white paper, which we've actually taken the opportunity to update. So check that on the website. It's on the product pages as well as under the additional downloads on the website. So check that out. And as always, as a follow-up to this, you're going to get access to the slides as well as the audio and video of me giving this presentation. And we'll also throw the white paper in the email to make sure that you guys have the most recent version of it. One other thing to keep in mind, of course, you can always call us and ask for training on something, whether that's transfer devices, these ELCDs, inverters, exit signs, emergency lights. We also do have an AIA course that we have two AIA courses that cover this topic as well as some other things. So we have an AIA course that's on sort of inverters and transfer devices and how they sort of fit together. We also have a more advanced course that goes into just the ELCDs and how they sort of fit within lighting control systems. And so there's a lot more advanced information in that one. You should probably take the inverter one before you take the lighting control integration one. But if you do want to do that, please reach out to either myself, Greg, or Matt. We certainly appreciate everything that you do for us. So if there's anything that we can do to support you, please do not hesitate to reach out. With that said, I hope everyone has a great 4th of July holiday. And for those of you who went to Light Fair, I hope you enjoyed that. If we were able to see you, it was great to see you. Otherwise, we'll catch you next time.